The second half of chapter 12 is on nonparametric simple linear regression. So remember, correlation, which is what we talked about in the first part, is linear. We talked about that in chapter 7, and we'll make some more connections here in chapter 12. And nonparametric linear regression leans on that connection. In fact, when we go to testing about slopes, we'll actually be doing Spearman's rho. And when we do confidence interval calculations for the slope, we'll really be doing Kendall's tau. And when we do prediction, which I don't talk about here in the vignettes, but is in the book, it leans heavily on Kendall's tau. Remember, the data are still pairs. And we assume a linear relationship, so that means that the expected value of y is related linearly through x with unknown intercept and slope parameters. But we're nonparametric. That means no statistical distributions, no epsilon errors, no sigma squared. Of course, there are still parameters, intercept and slope, so it's not nonparametric in that sense. It's nonparametric in the no distributions and no parameters involved in those distributions sense. So suppose we wish to test, we want to know the null hypothesis that beta 1 is equal to some value, probably 0, but actually we're going to do a different, a non-zero example here in this vignette versus the alternative that it's not that value, whatever value we choose. How do we do that test? Well, calculate what are known as zero intercept, or sometimes intercept free. Those mean the same thing, but sometimes people use one word or the other. Calculate these zero intercept residuals. So those are ui equals yi minus whatever you choose for your slope under the null hypothesis times xi. So these are a lot like the residuals from chapter 7, but an intercept is not involved. Okay, and you do this for all of the data pairs. Then use Spearman's rho on the pairs ui, yi. Okay, so we're basically taking out the value of the slope under the null hypothesis and seeing if there's any leftover correlation. The intercept doesn't matter for correlation, it's more about the slope. So we're looking at these residuals. We could use an intercept, but people just don't bother. And then we look for leftover correlation nonparametrically with Spearman's rho. Okay, so let's do this in R. I'm going to switch to a different data set. We're going to use the US precipitation data that has X's, which are time, or basically year, and Y is the number of inches of precipitation aggregated over the entire continental United States. There are 130 years worth of precipitation, and I like to make this plot. You'll find this in the book. So in this plot you can see that it's a highly noisy time series. So this is technically called a time series, but we're just doing a scatter plot, and I've connected them with lines so you can kind of see the evolution in precipitation over time. And the question here is the precipitation increasing over time? To my eye, it is, but specifically we're going to test for a 2-inch rise over the last 100 years on average, which translates into a null hypothesis of beta 1 being equal to 0.02. So the slope would be 0.02 over to result in a 2-inch increase over a 100-year span, which we're going to check against these 130 years of measurements. Okay, so beta 1 is 0.02. Then I calculate the zero-intercept residuals. So u is equal to y minus beta, times x. And then I get my r's. So I'm going to do rs u x. Oh, you know what? I've got a typo. It's not. I'm wrong in the notes. I got to go back to the notes and fix something. So the correlation is not between ui and yi. We're looking for leftover relationship in x. So we're doing a correlation between the xi's and the ui's. So I have a mistake in my notes. So let me just do that correctly over here in the code. So I'm going to check for a correlation between the x's and the u's. Method equals Spearman. Okay, so RSUX. There's a leftover small negative correlation, but that value is only meaningful when measured up against the sampling distribution. So we've got to go grab our Spearman's rho simulation. Okay, so we'll have to run it again because we have a different n, right? This code, we already have a bunch of samples of these RSs, but it was for the n in the earlier example. This n is different, so we have to rerun the simulation. But we can do the usual visuals. And AB line V equals RSUX. Okay, I don't remember how long this takes to run, but nope, it's done. And then we'll make this red. So I don't think we're going to reject this null hypothesis, but we can calculate a p-value. So that would be 2 times mean of rs less than or equal to RSUX. And 35%, so not enough evidence to reject the null hypothesis. So we conclude that a 2-inch rise over 100 years is plausible. So that is using Spearman's rho to calculate a test on a nonparametric regression slope. Now I want to pivot to talking about confidence intervals, which I said is going to involve Kendall's tau. And what I want you to observe here is that each concordant or discordant pair involves a calculation of rise over run, right? When we calculate concordant and discordant pairs, we look at yi minus yj divided by xi minus xj. So that's a change in y over a change in x, right? It's a delta y over delta x, so it's basically a slope. So let's call this Sij. It's the ijth slope calculated from the ijth pair of pairs. And we do this for we only do it for each unique pair, which means that we're going to force I to be less than j. And of course, there are n of those altogether. So this should result in n choose 2 pairs. We talked about that last time. So that's n times n minus 1 over 2. And let's call this ns. And this equality is going to be true unless we discard some pairs, in which case, if we do that, we might end up with fewer than n choose 2 unique pairs. But we don't have that problem in these precipitation data. But more on that in the book if you're curious. Okay, so let's do this calculation in R. Neat shorthand for calculating all slopes. So you can do a double for loop if you want to, but we talked about a couple vignettes back how an outer product can be used in lieu of a double for loop. So I want to calculate the outer product that involves differences in y's divided by the outer product that involves differences in x's. So this is a nice shorthand to calculate all 130 pairs of differences between x and y. But it overcounts. It makes a matrix that's 130 by 130. So prod 130. This is double, not prod 130, prod dim s. This doubles the number of pairs as what we get if we do n times n minus 1 over 2. So if we want to get just the unique ones, so we're not double counting the pairs, we can just look at the upper triangle of this matrix. So S upper tri S, and then NS, which is the length of S, should be equal to n choose 2, and it is. Okay, so really all you need is this part and this part, right? All this other stuff that I did is not really necessary. It's just to show you. I guess you need 3 lines, right? I need the upper tri, so I'll just delete the lines that I don't strictly need. So in these 3 lines, I can basically do the work of a double for loop to calculate all of the slopes that come from each pair of pairs. Okay. All right. Once you have the Sij, you must figure out which of these pairs lie near, which I put in quotes because we're only going to be able to work with the values that are in the data. We're not going to be able to get any quantile we want. So near the desired quantiles under Kendall's tau or the distribution for Kendall's tau, which we can get with the Q Kendall command or via simulation. So that is doing a for loop. So let's talk about that. We already have the for loop. We did it earlier. So we could just run another one of these using the n that comes in our data set. I do that in the book, but I'm not going to do that here. I'm just going to use Q Kendall here just to take a little bit of a shortcut. So quantiles of the sampling distribution for tau. So I want a 95% interval, so I'm going to do alpha is 0.05, and then Q is Q Kendall using the supdists package, and N. So I better run both of those lines of code. So 0.011 is that number. And now what I need to do is I need to figure out, I need to use this. So this Q Kendall output, the Q that I just got in the code, using this, I should say using, not use, with Sij that I calculated earlier requires rescaling the quantile, I still mean this, to indices 1 up to ns for S in my vector. So there are several ways that you could do this. So many sensible ways to use Q to map to 1 to ns. So here's what I'm going to do. I want a small index and a large index, or a right and a left index. So the large index, the right one, I'm going to get by taking ns and multiplying it by the quantile, but I'm going to add 1 and divide by 2 because my q's go from plus or minus 1, but my indices are only positive. So I'm shifting it up and dividing by 2 to get the right one, and then I'm going to do the left one is ns minus the right one. But this is going to give me fractions, so if I show you what that looks like, QL and QR. So that's indices 3,706 and 4,679. This time it does work out to not be, I think it's because the number of them is, NS. The number of them is odd, so adding 1 and dividing by 2 results in even numbers. So when we divide, it's not a fraction. But if you want to be careful to make sure it's never a fraction, you can write ceiling or round or something like that here. This is what I use in the code in the book. That doesn't change the indices in this case, but it would if you had an even ns. Okay, then I need to use those indices in a sorted S. So I'm going to sort the S's, and then I'm going to extract as my confidence interval the QRth one and the QLth one. So SOQL is the left or lower side, and SOQR is the upper or right side. And so my confidence interval is those two values in my slopes. Those bracket, according to Kendall's distribution, the lower 2.5% and upper 2.5% of slopes. So it goes from 0.0058 to 0.025. And notice that 0.202, which we tested earlier, is in that interval. Remember, the confidence interval is the inverse of a hypothesis test. So we weren't able to reject 0.02 with Spearman's rho, and we're also not able to reject 0.02 by the inverse of this confidence interval from Kendall's tau. And also, 0 is not in the interval. So we would also reject the null hypothesis that the slope is 0. So there's definitely an increase in precipitation, and it's reasonable to conclude that that increase is 2 inches over the span of 100 years. All right, the last thing I want to talk about is prediction. for non-P SLR, so prediction. A sensible setup, so it's sensible to use medians for everything. This is just one possible thing you could do. So what I mean by that is take as your estimate for the slope the median. This is the notation for median, the half in sorted order of slopes, and as the intercept, take the median of the y's, that is the half in sorted order of y's, minus what you just estimated for slopes, and then also take the midway or median value for the x's. So to be specific about that, what I mean is take your estimate as B1 to be the median of the 8,000 odd slopes that you calculated, and then take the median of the x's, and then there we go. And then your intercept is the median of the y's minus B1 times the median x value. And then I can put that on the plot. So I gotta get the plot back. So there is the plot that we had made before with the sampling distribution, but I gotta go grab the plot of the data. So visualizing, here's the plot of the data, and then I can do AB line B0, B1, LWG equals 2. And that is our estimate of the line for these data, whose slope is a little shallower than the 2-inch one, but there's definitely an increasing slope there. But what about uncertainty? So if you want uncertainty, that is a full prediction interval, you need to simulate and see the book for that. The only way to do it that I'm aware of is to simulate. And the code's a little bit long, so I'm not going to go through it here, but you can see it in the book. So I'm just going to conclude this vignette by writing in the notes. However, if you want uncertainty, like a prediction interval or a confidence interval on your predictions, remember chapter 7 where we made that hyperbolic curve or hyperbolic curves to represent our predictive uncertainty? You can get that with nonparametric regression, but you must simulate. And there's no closed form. Or math way. So see the book for that. So that's nonparametric simple linear regression.